All right, good evening, everybody. Tonight I'm going to do a real quick video on some general tips when multiplying fractions. The reason why I'm doing this one is because a lot of times when we're doing dosage calculations, or really anything that involves fractions, we have this habit of extending them way further than they need to be, and a lot of this can be done without a calculator if you know the proper ways to do it. So we're gonna start going. We're gonna do a little bit of old school, going back to algebra 2 in college if you took it. If you didn't, there's a couple of little bits of information that need to be known. For example, a, b, x, y, c, etc., etc. These are variables. Variables can are placeholders meant to represent any unknown number. So when we start looking at variables, as in when equations say things like solve for x, solve for y, solve for a, that's referring to a variable that can indicate an unknown number. So a lot of times you can use the variables in placeholder of something else if you're looking for a specific number. For example, if you're given milligrams per kilogram and you're given an amount in kilograms, for example, if say 2 milligrams per kilogram, and you're given a patient that is 4 kilograms, the answer here would be that you are looking for X number of milligrams, and there's your variable right there. So when we're starting to look at the rule of fractions, it becomes a little bit easier when you can think about it in terms of the fraction itself. So let's start with just a real simple one. We'll go a squared bc cubed over a b squared c. Now, this is a completely hypothetical situation. This doesn't refer to any specific kind of equation or whatever. This is just real basic stuff. So when we're looking at this, you can expand this out to say A times B times C times C times C. You can put that over A times B times B times C. And what this means is that when you have a number that's squared or a number that's duplicated in this manner, it just means that it is multiplied by itself. Now, the cool thing here is this is an easily reducible fraction. Whatever you have on the top, you can mark it off on the bottom, right? So we have B here and B here. We have a C here and we have a C here, which leaves us A C squared over B. So how we get from here to here is literally just taking like terms on both the numerator and the denominator and crossing them out until you have a disparity in the amount of terms. For example, if you have two A's on the top right here, but one A on the bottom, you can mark out one of those A's, but it still leaves you one A in the top. Let's do another one, something a little bit more extensive, all right? So let's say that we have A squared B over 1 times 1 over C squared B. Now, what this means is that from the fraction, from the properties of multiplication, this is literally just the same as saying A squared B over C squared B. It's the same thing because these two numbers, they cancel each other out, all right? Even if they didn't, what this would really be is A squared B times 1 over 1 times C squared B, okay? We all see that. 1 over 1 is always going to equal 1, so the answer is going to be here in A squared B over C squared B. And then you can reduce that even more by just canceling out the B's until you get A squared over C squared. These are real easy steps for fractions that allow you to reduce the fraction really quickly without having to run all of these numbers in a calculator if these were numbers, okay? So instead of using variables, let's do actual numbers. So let's say that we have 10 over 24 times 4 over, I don't know, 17, a ridiculously odd number. And then we have 5 over 100 times 12 over 9. So at first, this equation looks like a hot mess. And for the most part, these are messy fractions. Some of these are compound fractions or irregular fractions. But if you draw the line straight across, it still starts to look like the same thing that what we're used to, all right? So we have 10 times 4 times 5 times 12 over 24 times 17, a ridiculous fraction. I should not have used that number, times 100 times 9. Now, whether you see it or not, there are some like terms that you can reduce here, that you can get rid of before having to plug all of this into the calculator. And in truth, if you do it like this, you may not even have to use the calculator in the end. For example, 10, we have a 10 here, and we have 100 here, right? Well, you have zeros there, so you can mark off those zeros. And now you have, instead of 10 times 4 times 5 times 12, you have 1 times 4 times 5 times 12. Well, when you multiply anything by 1, it doesn't really matter. It's the same number. The same thing here. 12 over 24, this is really 1 over 2. So now we have 4 times 5 times 1 over 2 times 17 times 10 times 9. Okay? You can even go another further step here. You see 4 and 2. 4 divided by 2 is equal to 2. So now we really have 2 times 5. You don't have to worry about the multiplying by 1. Times 17 times 10 times 9. Okay? Now, if we look again at the top, we have 5 times 2 is 10. So now we have 10 at the top, 17 times 10 times 9. We have two 10s that are able to cancel out. So in truth, the only equation that you have to do is multiplying 17 times 9. So from here, 17 times 9 simply just becomes a multiplication problem. And 17 times 9, 17 times 9 is 153. So that's 9 times 7 is 63. 9, 10, 11, 12, 13, 14 is 15. It's 153. So the answer then becomes, instead of 1 over 17 times 9, it becomes 1 over 153. Now, this is it's just an example. This is just, hey, this is how you work. This is how you can work with fractions or reduce fractions without the use of the calculator. So there are a couple of things that we have to take into consideration. When doing dosage calc, you're not going to always have a calculator around with you. Like, if you're a nurse, when you get there, you're not going to be like, I'll probably carry around a calculator in my pocket simply because I'm a nerd. But not everybody's going to have a calculator. So you have to be able to look at dosage calculation equations and be able to resolve them and solve them without necessarily using a calculator. So let's take a look at a different one. We're going to start with a sample question from nurseslabs.com. I'm going to start with number 1 from the parental dosage calc quiz bank. And the question is, a healthcare provider prescribes kanamycin at 7.5 milligrams per kilogram intramuscular every 12 hours. Available is kanamycin 0.35 grams per milliliter. And how many milliliters will you administer for each dose to a patient who is 157 pounds? Now, when you're looking at dosage by weight, it doesn't really change. Everything essentially gets multiplied by everything else. So we're looking at 7.5 milligrams per kilogram, right? Then we multiply that by, 1 kilogram is equal to 2.2 pounds. Then we have a patient who is 157 pounds, right? There's my little patient dude. And what we have on hand is 0.35 grams, which is really 350 milligrams. But I'll spell it out. So we'll do, we have 1,000 milligrams is equal to 1 gram. And then we have 0.35 grams per milliliter. So when we start looking at this, we can take a look, and if you spell this out all in long ways, keeping everything on the top line and on the bottom line and only having one long equation, you can treat each one of these little pieces right here as a variable. Okay, so we'll say 7.5 times milligrams times 1 times kilograms times 157 times pounds times 1 times gram times 1 or times not times 1 times milliliter. Okay, and then we draw our line, my squiggly line. Then we say kilograms times 2.2 times pounds times my little dude times 1,000 times milligrams times 0.35 times gram. So each one of these becomes its own variable of sorts. So let's look and see where we can see the same variable on the top as we do on the bottom. Well, the first one that jumps out is milligrams. So we're going to cross off milligrams. Here's grams, so we're going to cross off grams. Here's pounds, so we're going to cross off pounds. And here's kilograms, we're going to cross off kilograms. So now what we're left with is 7.5 times, we don't have to worry about the 1, because whenever you multiply by 1, it's the same thing. You can automatically cross out all 1s when they're by themselves. So 7.5 times 7.5 times 157 times milliliters over 2.2 times my little dude times 1,000 times 0.35. Let me stick with a standard of multiplication symbols here. So what we're going to be left with is 7.5 times 157. Let me get my calculator out again. That's 7.5 times 157. On the top, that's going to be 1,177.5 times milliliters over 2.2 times 1,000 times 0.35 is equal to 770. The little dude is the same as a 1, so you can just disregard the little dude. And you're going to have 1177.5 divided by 770. And the answer is 1.529 milliliters. And it's probably going to round us up to the 10th, so we'll do 1.5 milliliters. All of this is done because you can treat each one of these numbers as if they are a variable, A times B times C, or ABC over CBA, right? It makes it a whole lot easier when you can think about it in this fashion, because the numbers tend to be a little bit more easier to manage, easier to digest when you treat them in this way.